A recent study has investigated teleparallel gravity and its potential to resolve the tension surrounding the expansion of the universe in a way that general relativity can't. In the early 20th century, our understanding of the universe was turned upside down when observations made by Edwin Hubble revealed that the very fabric of the cosmos was stretching. At the close of the same century, this realization became even more complex when two separate teams of scientists discovered that not only is the universe expanding, but the rate of this expansion is accelerating by observing distant supernovas moving away from Earth. The cause of this acceleration remains a mystery and has been given the placeholder name dark energy. The best current explanation for it is the cosmological constant, which accounts for a form of background energy called vacuum energy. The rate of the expansion of the universe is known as the Hubble constant. It describes the proportionality between the distance of a galaxy from Earth and the velocity at which it recedes. This has been a headache for physicists because the two major ways of determining the Hubble constant are in vast disagreement. This issue is dubbed the Hubble tension, and one way to explain it could be by extending our current best model of gravity, general relativity, posited by Einstein in 1915. A paper published in the journal Physics of the Dark Universe by Celia Escamilla Rivera, a cosmologist at Instituto de Ciencias Nucleares, Universidad Nacional Autónoma de Mexico, and her co-researchers attempts to tackle dark energy and relieve the Hubble tension. We found that by using gravitational models extended beyond general relativity and new cosmological datasets, such as observations of distant quasars, we can confront the Hubble tension and the dark energy issue at local scales, says Rivera. Using numerical and computational methods, we performed analysis using different proposed models in teleparallel gravity tested with two different cosmological samples that measured distances in the local universe. Teleparallel gravity is an alternative theory to general relativity, also devised by Einstein. This other theory of gravity uses a different recipe of equations to explain gravity without the curvature of spacetime and seeks to unite it with one of the universe's other fundamental forces, electromagnetism. Recently, teleparallel gravity has been gaining popularity due to the promise that it could solve the cosmological issue related to the Hubble tension and could explain the nature of the late-time cosmic acceleration without invoking a cosmological constant, Rivera says. Rivera and her colleagues tested the parameters of this alternative theory of gravity using two new datasets of distant and highly redshifted quasars, the bright regions at the heart of galaxies powered by feeding supermassive black holes observed in ultraviolet, X-ray, and visible light. We are interested in the subject because teleparallel gravity is a suitable candidate for an alternative proposition to general relativity that solves different cosmological issues, as well as having some interesting theoretical properties, Rivera concludes. For a wider audience, it is interesting because we are testing alternative proposals to general relativity to better understand the universe. For experts in the field, it is an update to the state-of-the-art regarding specific models in teleparallel gravity, also using relatively new quasar samples at high redshifts.